Intro to Deep. Hello, everyone. So I'm extremely happy to welcome Dr. Deep Chatterjee. Deep is actually um, involved in a lot of gravitational physics, gravitational waves, and discovery of gravitational waves. He was, if I'm not wrong, he was involved in the LIGO project, which went on to win the Nobel Prize. It was a very long project, like a 60-year project or something. It was proposed quite a long time ago, and then people waited for quite a long time, and then a lot of stuff happened. And I think in CERN they discovered this first signals of gravitational waves using the detectors that they have created. So right now, Deep is doing his postdoctoral research in UIUC, that is University of Illinois Urbana-Champaign, and he is involved in a lot of cool stuff that is related to understanding how our universe works, I think. So let's learn from Deep. Thank you for coming, Deep, and you can start whenever you're ready.
Okay. Yeah. Thank you. Thanks, Ashwini. Thanks for having me. So today I'll tell you this story about gravitational waves, which were discovered back very recently in 2015, and then a more recent emerging field of multi-messenger astronomy and what that is. So like I said, please, I'm assuming that that probably Showdown will take a look at the chat and keep a track of questions. So we'll take a look at that at the very end. But keep those coming. So today, let me get started. So we'll talk today about gravitational waves for sure. But before that, let us start with a history of gravity. And whenever we talk about gravity, the two big names that show up are the two big giants that show up are Isaac Newton and Albert Einstein. So we will talk about them briefly, and we'll find or rather not that we'll find, but we already know. So we'll just talk about some of the shortcomings of Newtonian gravity. And so if you ask, was Newton right? Well, for the most part, yes, because Newtonian gravity, as we study it in school, it is able to explain a lot of the stuff that is happening in the universe, like celestial mechanics. But then there are small things that it does not explain. So we'll take a look at that. So if you ask me, was Newton right? I would say yes, in a certain regime, but then not quite. And we will know what Albert Einstein had to add to it to fix some of those issues and to predict additional observations. And we will take a look at that. And so if you ask me, is Einstein right today? And a carefully crafted answer probably is that certainly more than Newton. And if you ask me why, then I would say, well, there are other observable evidences, at least standing today. General relativity is pretty much present in our practical lives as well. The GPS that we use, the spacecrafts that we launch, they need to take into account corrections due to general relativity. But for the sake of today's talk, what we'll focus on is the existence of gravitational waves and the observation of gravitational waves. And it's been a long journey, as Ashwini alluded to, that were predicted back in 1916 and were observed in 2015. So it has been a century-long journey to find them. So that will be the first half of the talk. And then in the second half of the talk, I'll talk about multi-messenger astronomy. What that is, as the name suggests, is doing astronomy, that is observing the same source using multiple messengers. In this case, those multiple messengers are gravitational waves and electromagnetic waves. So that is light simultaneously. So we'll talk about that. And finally, and I'll also tell you why it's exciting. And then finally, I'll tell a little bit about the research landscape today, some of my own work, and maybe if we have time, we'll just spend a few slides on few other thoughts on education and research. But before we get started on that, I thought I would just tell a little bit more about myself. I did my integrated bachelor's and master's from IISER Kolkata. And from then on, in 2015, I moved to Milwaukee, Wisconsin, where to do a PhD. And that's where I started working with the experiment that Ashwini talked about, LIGO, which is a ground-based gravitational-wave detector. And more recently, in 2020, I graduated and moved here in Illinois as a postdoc at NCSA. But more importantly, I am a friend of Ashwini, the founder of Cheenta, and he's an amazing person. I'm really lucky to have known him. And we just happened to overlap during this phase, during the 5 long years in Milwaukee. We just happened to be at the same place and time doing the same thing, which is a PhD. And because I do get this question sometimes, that is, why does it take so long to do a PhD? So I found this really amusing PhD comic, which I thought I would share broadly today. So for a PhD, you need to do research. And when you start doing your research, well, first of all, you have to find a problem. But then once you do, the picture at the outset probably looks something like this. There's a nice workflow. Of course, the steps might be different depending on what field you're in, but it roughly looks something like this. But if you delve a little deeper, what you start realizing is the real picture is more like something like that. And that's really intimidating at the beginning, and therefore a lot of time simply goes away in understanding each of these individual components and maybe these connections between the individual components, and hopefully by the end of the time, as you would have understood that and translated all of that back into this, and so that's what really consumes your time as a PhD. So I just thought it was amusing and just share with people over here. All right, so let's get started. So today, let's start off with the story of the apple. And I'm not talking about the Mac or the iPhone, but rather the apocryphal story that an apple fell on Isaac Newton's head, and all of a sudden he knew what gravity was. That the fact that it behaved like this inverse square law. Probably, I don't know how much truth is there to that story, but one way or the other, he did discover the law of gravity. And while that equation may seem seemingly simple, with that he was able to explain a lot. He was able to explain celestial mechanics. A lot of observation had been done back in the day, which was not there was no mathematical explanation to that. And with his law of gravity and with the techniques of calculus, he was able to explain that. He was able to explain the fact that planets go in elliptic orbits, and some of the other empirical laws like the Kepler's laws of motion, and at the same time other phenomena like tides. So then one might ask that, well, what was the problem then, right? So now what happened is that even back in the day, there were small things that Newtonian gravity could not explain. And one of them is this. It is illustrated in this figure, but this is called the periastron precession of planet Mercury. So it's known for a long time that while Newtonian gravity said that planets should move around in elliptical orbits, it turned out that Mercury's orbit is not a closed ellipse, right? So what happens is Mercury completes an orbit every 88 days. But then every time it comes back, its periastron, which is the closest approach to Sun, it moves by a tiny bit. And this tiny bit is really tiny because it cumulatively over a century only about 43 arcs of a second. And just to give some context, a degree divided into 60 is a minute, that further divided into 60 is a second. So 43 arc seconds over a century is really a small amount. But then on astronomical scales, it's significant, because if you think about it, the moon, which is a fairly large object in the sky, is about only half a degree. So it's about 30 minutes. And then stars typically are of the order arc seconds. So 43 arc seconds is a decent amount of change, even if you think about astronomy that you can do with the naked eye. And so that had been recorded for long centuries, and there was no clear explanation to that. But then there were more issues, and those issues showed up on seemingly different sectors of physics, like electricity and magnetism. So let's talk about that a little bit. So we are all familiar, and I'm assuming that once again, I'm thinking of high school students over here. You may have already encountered the Coulomb's law in your textbooks. Even if you have not, you might do really soon. And if you ever wondered that, well, the law of gravitation follows like a 1/r² dependence. The force between two charges also follows a 1/r² dependence. So then, is there a similarity between electricity and magnetism, and then gravity as well? And turns out that there is, and that's something I will allude to in a little bit. But then this equation is really true when charges are at rest, and that's why the term you would hear in your textbooks is electrostatics. Electrodynamics, on the other hand, which is only partly in the school curriculum, involves charges in motion and then time varying fields. And the reason why I say partly in school curriculum is because you will probably have encountered electromagnetic waves, and even if you've not, you will probably encounter it. And the fact that light is an electromagnetic wave, and then it involves varying both electric and magnetic fields. So you can't have just one to have an electromagnetic wave. So you need both. And so electrodynamics, which was mostly formalized by Maxwell and others back in the day, basically it the bottom line was that if you have dynamics, then there is not a very clear divide between an electric field and a magnetic field, but you have to treat them together as one electromagnetic field. And then variations in that electromagnetic field propagate out at the speed of light. So the very important consequence of electrodynamics was that there was electromagnetic radiation. And that is something that fills our everyday life today. All telecommunication, your cell phone, your Wi-Fi, your food, you cook food using microwaves. Those are some of the artificial sources. But then there is the sun, which is the key to life, all of which depends on electromagnetic radiation. And so, while the formulation of electrodynamics was mostly on, starting with fields, but then if you ask that, well, now the fields would have to, arise from really particle motion, which are in turn described by, Newton's laws of motion, F = ma, basically. Now, when you go ahead and try to do that, it turns out that there is this inconsistency between particle mechanics and electromagnetism. And that had been known back in the day. There were other minds, not just Einstein, but people also trying to find a resolution to this problem. But it was really this work by Einstein, which really deals with electrodynamics of moving bodies. It was in German. But it was really this work on the electrodynamics of moving bodies, Einstein in 1905, that corrected some of the issues that were present back in the day. And then, although the word relativity is not mentioned anywhere over here, this was basically the special relativity that we talk about today. And just a fun fact, one of the very first English translations were actually done by Bose and Saha, so it does have a Kolkata connection there. Okay, so now, the special in special relativity has to deal with the fact that it's a special case, meaning you deal with frames that are moving at uniform velocity with respect to each other. There is no acceleration that is considered. Okay. Now, going from that to general relativity took quite some time, although it may seem simple, but turned out that it was actually not that simple, and it changed the way we think about gravity. So over the next decade, Einstein would work with his childhood friend, again, eminent mathematician Marcel Grossmann, reusing some of the mathematics that had been developed previously, again, by eminent mathematician Riemann. And here, one of the key differences, I would say, between Newtonian way of thinking about gravity and Einstein is the idea of free fall. So in Newtonian gravity, you would think that if a particle is falling freely on Earth's gravity, then it has an acceleration of the order 9.8 meter per second squared. And that is in sharp contrast with Einstein's idea about what free fall is. So according to Einstein, a body in free fall is really not accelerated. So if I'm put in a closed box and put in outer space, my feet don't touch the surface of the box, then I have no idea of distinguishing that scenario from the case when I'm in free fall on Earth's gravity, in which case my feet don't touch that box at all, which is also in free fall with me. So this idea that gravity is indistinguishable from acceleration basically formed the basis of general relativity. And so as I was saying, that while in Newtonian sense of gravity, I sitting in my chair, I'm not in free fall, but according to Einstein's theory of free fall, I am actually an accelerated observer. I am so there's a force acting on me, which is the normal force of this chair, but gravity in fact is not a force, but it comes from the curvature of space. So going from 1905 to 1916, there were several setbacks that Einstein did have to face, which included incompleteness in his proofs, a hasty competition from, again, mathematical giant back in the day, David Hilbert, but then eventually, there it was, the foundation of general theory of relativity, generalized theory of relativity, once again in German. I'll share these slides sometime so that you can have a look at these links. But that was the final product. Okay, so in the years ensuing 1916, whenever there is a new theory of gravity, it has to pass certain tests, right? So in this case, of course, the very first check that GR passed, and I'll go back a few slides, is to solve this problem of perihelion. So in Newton's gravity, the planetary orbit had to be a closed ellipse, but that was not the case in general relativity. In particular, there could be precession, and it turned out that based on GR, this perihelion precession of Mercury was predicted exactly. Okay, So once again, if you think back, if you look back at my slide, so I was talking to you about electrostatics versus electrodynamics, and it turns out that in case of electrodynamics, um, the equations are described by what are called Maxwell's equations, and they reduce to this Coulomb's law in the case of electrostatic case, when charges are at rest. But then the same thing happens in the case of general relativity, that if you have slow motion, or if objects are at rest, general relativity also reduces to Newton's law of gravity. Okay, so that's the extra addition that you make. So after 1916, there were several observational evidences. So one prediction of GR was the fact that light would be bent by gravity, and that was in sharp difference with what Newton would have said. And that was confirmed by Arthur Eddington in his famous 1919 experiment, where he took his team to Obral, Brazil, and observed the stars that threaded the region around the sun. And he did measure the deviation, and it did conform to predictions given by general relativity. And then in 1916, immediately Carl Schwarzschild solved the GR field equations and predicted the existence of black holes. Einstein applied general relativity to cosmology the year after, so there was a lot of activity going on. But in 1916, Einstein also showed that general relativity would have gravitational waves, very similar to your electromagnetic waves that is predicted in electromagnetism. So whenever you would have accelerating masses, you would have these gravitational waves that would very analogously take energy away from the system, just like electromagnetic waves do. But unfortunately, there was not much attention that it received. In fact, and part of the reason could be attributed to the fact that these were weak. Gravity manifestly is a very weak force. You can, whenever you're picking up something, you're essentially defeating the entire force with which the Earth is pulling that object. But just to give an order of magnitude estimate, the Earth going around the sun gives off only order 1 watt of gravitational waves. So if you think about it, if your tea goes cold, you put it in the microwave, which is order, say, 600 watts of power. You heat it for about a minute, and the tea is hot. But if you had a machine that magically somehow converted all your gravitational wave energy into heat energy, and you use that to heat a cup of tea, it would take you order 10 hours to do the same thing. So the point is, they were extremely weak, and then Einstein even went ahead to write about their non-existence, and then eventually reverted his claim back after a few years. So overall, while other topics, the other GR predictions did receive attention back in the day, gravitational waves were largely ignored for a large part. And a part of that could also be attributed to the fact that the war broke out back in the time, and the best minds had to focus on something different. However, there was renewed interest in the 60s and 70s, which is in fact called the golden era of general relativity, and people started to understand the physical effects of gravitational waves. What effect would these waves have on matter? Like, what would be the observer? Like, how could we measure gravitational waves? And the conclusion was that gravitational waves cause strain in things that they pass through. So strain is, again, this is a dimensionless quantity, but it's essentially, it would change things by a small amount like if you have a rod, then it would change the length of the rod only by a certain amount, and that change would induce heat in that rod, and potentially you could measure that, or you could in some other way measure that difference in length, and thereby have a measurement of gravitational waves. And so that idea was picked up by Joe Weber when he set out to make these bar detectors. The idea was that if a gravitational wave came through it, then it would change that length. And by means of putting these very sensitive piezo crystals on this bar detector, you would be able to pick up those and put it in seismic isolation and such. But unfortunately, that was not sensitive enough. Gravitational waves were still too weak to measure. There was indirect evidence. So just like in a classical atom, the reason why it cannot exist is because if you have an electron going around in an atom, then it's an accelerating body. It would emit radiation, and then eventually the radiation would take energy away and it would fall down. So the same idea is true for gravitational waves. In fact, that is what is measured. I do hear some static on the line, so maybe someone is unmuted, but I'll keep going. So there was indirect evidence of the existence of gravitational waves. So here, okay, I'll just keep going. So there was indirect evidence of this fact that gravitational waves do carry energy away, and that came from observation of this binary pulsar in the 70s. So here, this system was a binary system where one of the objects is a so-called a millisecond pulsar, which basically is an object that gives off bursts of radio signals periodically. And by studying this pulsar, because if one of the objects is a pulsar, and if it goes away, then there is a little bit of a Doppler shifting, and when it comes to you, it's a little blue shifted. So there was this periodic variability in this system through which you can actually measure parameters like how much are the masses of the system, or what's the radius of the system. So and what they found was that with time, and note that here on the x-axis what I have is the year. So you started the measurements all the way back in the 70s, and the observations continue even till date. And the orbit has been essentially shrinking. So this is essentially the time to reach periastron, which is related to the fact your orbital parameters. And so it has been known that the Hulson-Taylor pulsar has been shrinking. And when you did throw in the general relativity prediction based on what the masses of the system were, it's a perfect match. And this was compelling evidence that gravitational waves did exist, but then there was no direct evidence. This was still an indirect evidence. But nevertheless, the 1993 Nobel Prize did go to Hulson-Taylor for this discovery. And like I said, the observations of this pulsar continue even till date, and there is near perfect match with emission from gravitational waves. So I told you a couple of slides back that gravitational waves are manifestly weak. So what is it that you need for for like a good burst of gravitational waves that you can detect, right? So clearly, the Earth-Sun example, it's too weak. But what you need, and here I have physicists often like to do an order of magnitude estimate for things they wish to measure. So an order of magnitude estimate for gravitational wave luminosity is given by something like this. So you have a note over here. This number V over C is a dimensionless quantity. This quantity, which is essentially which is called the compactness, this is also a dimensionless quantity. So here, essentially, the energy scale is set by this fundamental quantity C to the 5 over G. So this is a fundamental quantity that sets an upper limit of gravitational wave emission. So this is the maximum. So any system that you have in the universe, you cannot have more than order 10 to the 52 watts. Just for comparison, the sun only emits 10 to the 26 watts. So that's a lot. Even though gravitational waves are manifestly weak, but if you did have systems which were compact, right? So if you think about M and A, M is a typical mass of the system, and A is a typical radius. So if you had large masses put in a small radius, or in other words, if you had a compact system moving at very high speeds, then that would produce a significant amount of gravitational wave emission that potentially could be detected. So indeed, therefore, the only contenders are your black holes and neutron stars. So black holes are the most compact objects, and then neutron stars are very close to black holes. And those are the objects that are detected today in terms of gravitational wave candidates. All right, but even then, these are very weak. So although this is a large amount of energy, but if you think about it, other types of explosions in the universe also dump similar order of magnitude energies, like supernovae or gamma ray bursts. Maybe there is one or two orders of magnitude here and there, but roughly there are explosions in the universe that dump a similar amount of energy. But then, irrespective, because the strain that I talked about, it falls down as the waves are traveling. The typical strain that is expected to be produced on the Earth is really tiny. And if you go back a couple of slides, then the strain is essentially proportional to it's a relative change of length, right? So what 10 to the minus 21 means is that if you have a 1 meter rod, that will only stretch by 10 to the minus 21 meters, which is a billionth of a typical Bohr radius, right? And so how do you go about measuring that? So no wonder those bar detectors did not measure such a small change in length. So here I'm going to play this video. So the solution to that is interferometry, which is again something you may have seen in your textbook. So here the idea is that you have a laser which sends light off, and you split it on a beam splitter. It comes back, and using the interference of the light, you are able to find out this relative change in length. So here, for example, usually if there is no gravitational wave, the way this operates is that there is a destructive interference initially, but then as a wave comes by, it produces this change in length, and that changes the interference pattern, and that's the fundamental principle on which gravitational waves are detected. Now, clearly, if I told you that is the model, then that would be wrong. A big fat lie, really. In fact, the model is fairly more complex, and in reality, the instrument looks something like this, where you can identify parts of this simple setup, but in reality, there is fairly a good bit of complex instrumentation that is built into it. And so just gonna okay, great. And so it was this idea of using laser interferometry that took off in the 70s, and it was found to be a viable candidate to actually measure these gravitational waves, and that led to the proposal of the laser interferometer gravitational wave observatory. Here you can see a snapshot. So whenever you propose an experiment, you have to make you have to show evidence that this will work, and you have to convince several people to actually pay you a lot of money, and that might, although it might seem a lot, it's really a fraction of most countries' military budget, but it does extremely cool science. So in 1989, this proposal was put forward to the NSF, and it eventually got funded. It led to the construction of these very long baseline interferometry. So each of these arms, so the same arms that you saw over here, that's that over here. These are 4 kilometers long. One of them is in Hanford, Washington, in the U.S. This one is in Livingston, Louisiana. And so these were so this is what LIGO is, and there's an analogous detector called Virgo in Italy, and there's a Japanese detector that is coming online right called Kagura, and in a few years there would be LIGO India as well, which is a collaboration between the US and India to set up a gravitational wave detector in India. All right, so then so of course the construction of LIGO began in the early 2000s, late 90s, 2000, but it's not that you build that detector, you turn it on, and there you have a detection. It did require several science runs, several upgrades to the detector over the early 2000s to finally have what is called advanced LIGO that turned on in 2015. But it is true that in 2015, when the detector did turn on, there was the evidence of gravitational wave. In fact, the signal was so loud that here, you could actually measure that interference pattern directly. So you can actually see it. Usually the signal is really weak and you have to do sophisticated data analysis techniques. But for the first event, it was loud. And you saw the same signal in both detectors, those two that I mentioned, Hanford and Livingston. Both, the thing with gravitational waves is that because it's coming from a distant object, it would affect both these observatories modulo the light travel time between them. But there it was. Okay, and for that discovery, this particular event was from a binary black hole system at about order 400 megaparsecs away. 1 megaparsec, for reference, is roughly the distance between us and the closest galaxy, Andromeda. So this is significantly more distance away from that. But for this observation, the 2017 Nobel Prize went to people who had envisioned of LIGO that involved Barry Barish, Kip Thorne at Caltech, and Ray Weiss at MIT. You may know of Kip Thorne from the movie Interstellar, because he was someone who was involved with some of the simulations that went into Interstellar. Okay, so here this is a simulation again of what a binary black hole merger could look like. In reality, you don't see this. Okay, these are you don't see a system like you cannot use your telescope to see something like this, because these are really far away and in a galaxy cluster. But that's roughly what it should look like based on numerical calculations. I'll just play it one more time. So you have the warping of space around, and as the as the black holes merge, you can see farther out there is warping of space as the waves propagate out, and then eventually, as the black holes merge, they settle down into a final remnant. And here I'll just pause the video. A few cool things to note is the so these two are the same images. For example, it's just coming from the fact that one of them comes directly at you, the other one actually comes from behind a black hole. Okay, great. So this was great, but then what was next? So now that you have detected gravitational waves from a binary black hole merger, the next candidate would be to observe a binary neutron star system, and here the difference is shown in this video. So if you have a binary black hole merger, in that sense, is a very uneventful event because nothing really happens. But if you do have a binary neutron star system, I'll play the video one more time. You have these neutron stars going around each other. They do emit gravitational waves during the inspiral phase. And when they merge, because these are neutron stars, right, they have, there's a lot of debris that is flung out. And because this is neutron-rich matter, you have what is called the R process, synthesis of heavy elements. So what happens is you form very unstable and heavy elements very quickly, and because they are unstable, they decay via radioactivity, and that produces a lot of heat. I'll just play this one more time during the merger phase. So it produces a lot of heat, in this debris, and that essentially powers an explosion, similar to any other explosion that you may heard of, a supernova, which is essentially a star going, bursting in the final stages of its life. But in this case, it is really the radioactivity that powers this. And so you see the gravitational waves, but at the same time, you should be able to see this explosion in light, right? And that is what was observed in 2017. And this is, again, going back to what I was talking about, multi-messenger astronomy, that you have this system. I'll just forward the video a little bit over here. So in 2017, there was observation of gravitational waves from a binary neutron star system. But then, because it was a binary neutron star, it produced this explosion. And then when telescopes, went up, in this case, this cartoon shows the Hubble Space Telescope. Of course, I mean, once again, this is an artist's impression of the entire thing. But there is, if the telescopes, they look for the region of the sky from where the signal came from, they'll probably be able to find this explosion. And in this case, I'll just pause the video right there. It was that little thing was this kilonova, this explosion that I just talked about. Now, in reality, these videos are mostly artist's impression. Real data never looks like that. In fact, it's not at all as dramatic as is eventually shown in these artists' inception. Real data looks something like this. So this is like an actual image taken of this galaxy called NGC 4993 about 20 days before. And then, after this event happened, SWOPE is the team that first detected this object, and you can see that after difference imaging, that is your discovery. Okay, and so why is this exciting? Just move ahead. And so why is this exciting? Well, this is the very first time that you have a coordinated effort towards observing these explosions. So you see gravitational waves from a particular instrument, LIGO in this case, and then you pass on the discovery information to your telescope facilities, which then scan the sky and then find the transient. So it's really the very first time that we are seeing such a coordinated effort towards doing astronomy. But then, even if you leave that out, there's a lot of fundamental science questions that a multi-messenger observation like the one that I showed you that answers. For example, you may know that the iron nuclei is the most stable nuclei that exists. It's really hard to synthesize by natural processes elements beyond iron. So it had always been a mystery that in the universe, the elemental abundance of elements beyond iron, where do they come from? There was this hypothesis that it does come from compact object mergers like binary neutron star mergers, but this was the very first time we actually had direct observational evidence for that. Okay, so if you think about gold, all the golds that's produced probably came from mergers of these compact objects, because there is no other energetic phenomena in the universe that could produce heavy elements like gold and platinum and such. And then it also answered fundamental questions about the nuclear properties of matter. So we know that when we say a neutron star, of course, the neutron star is not entirely made of neutrons. There is more to it. And then finding those properties of nuclear matter out can be done from observations of both gravitational and electromagnetic waves. So it turns out that this whatever the neutron star is made of, it leaves an imprint in the gravitational wave signature. And also from all the debris that comes out, the subsequent explosion that depends on the properties of that explosion depends on what the neutron star was made up of. So it really answers those fundamental questions about nuclear matter, which is astounding, because you may think that nuclear matter is essentially something very microscopic, but then you're using these astrophysical laboratories like binary neutron star systems to detect them, to find answers to them. And then if I go back and play this video one more time, then at just the instance of merger, and I will just take the video a little forward, you notice that right when the binary is merged, so right there, there's this burst, there's this jet that is released, and that's called a gamma ray burst. Just go ahead. So it had been a long outstanding questions regarding what could cause a typical type of gamma ray burst called short gamma ray bursts. Short gamma ray bursts have been observed for a really long time, but then what are their progenitor systems? That was a long-standing question, and this was again the first time that you had direct observational evidences that it is these binary neutron star mergers that give rise to short gamma ray burst. Correctness of general relativity. General relativity predicts that light and gravitational waves, they travel at the same speed, which is the speed of light. There are other theories of gravity which could say that there is a difference in the speed of gravity and the speed of light. And then what this event showed was that at least as of now, general relativity still stands the test. Because in this case, that gamma ray burst and the gravitational waves, they reached you almost at the same time. And there are also fundamental questions about cosmology, which I'll get to in a little bit. Now there is, if you, and this part of the talk, I'm really focusing on, what's the landscape today. So between 2015 and 2020 or 2021. Gravitational wave detections have increased dramatically. So in these gone 5 years, the number of detections have grown pretty sharply. You had 3 events in the first observing run, 10 in the second observing run, and in the more recently concluded observing run, there have been order 50s, 50 or so events that have been observed. So really, we have moved from the discovery phase to the astronomy phase, when events are routine in these 5 years. But it turns out that video that I showed you, that's the merger of two neutron stars giving off light. Unfortunately, there has been only one discovery till date, and that event, GW170817, remains the only successful EMGW candidate. And part of the reason is because they're difficult to discover. So here, what I'm showing you is, again, actual observational data. On the y-axis is what is called a magnitude, but think of this as a flux. And on the x-axis is essentially time. You can read the lower axis over here. So this event happened on 17th of August, 2017, and so this date is essentially the 19th and 22nd of August. So just a few days after the event. And what you notice over here is that before that, let me say a little bit more about this. So here, so let's just ignore the data points over here, but only focus on these solid curves over here. What these are essentially the flux, which is the y-axis, in different filters. So when you have a telescope, the telescope does not see all throughout the spectrum, but only a certain part. Maybe it sees the red part, maybe it only filters red light or green light. And or maybe UV light, which is what these curves are. So here U refers to ultraviolet, and then if you go up, you have GRIZ, which are basically green, red, infrared, and such. So what you notice right away is that these objects fade really fast, and then they fade very quickly in more so in the bluer bands as compared to the redder bands. And that's again expected if you think about your black body physics. Then a higher temperature is associated with radiation being emitted at a higher frequency. So the hotter an object is, the more bluer it is, and as it cools down, it becomes more red. So that is exactly what happened with this kilonova. You have when you have it initially, you have it very hot, and as it cools off, the ultraviolet bands sort of fall down. They fade really fast, but then the infrared bands, they sort of peak a little later, and they stick around. In fact, if you look in radio, the emissions last for over a year. Okay, but then if you're interested mostly in the optical bands, things that you can see, right, then it becomes a challenge because these are extremely fast transients. So if you don't discover them within a day or maybe a few days, then they will become too fade, to claim discovery. So they are intrinsically dim. The name kilonova means it is less bright than a supernova. So they are intrinsically dim, and also they fade real fast. So then one of the challenges today is actually to build tools and have this communication between say the gravitational wave facilities and the partner facilities like telescopes and gamma ray burst GRB facilities to actually to enable discoveries like this, because after that event the community has realized that doing these detections by chance it's not possible. You really need to have a coordinated effort to achieve success. So that leads to something that I work on. So I mostly work on this effort of connecting gravitational waves with electromagnetic events. So the EM counterparts that you can observe. So I work specifically within LIGO, or I work on the alerting infrastructure. So once a wave is detected, you need to have certain data products that tell you that yes, this is of potential interest. This is this is worth follow up. So that is something that I work on. I also work on the infrastructure required to actually communicate that information to partner facilities, so that you can send discovery information like this. For example, this is an event that happened on the 15th of January 2020, and what is I feel lucky to be giving the talk right now, because it was only 2 days back that the LIGO Virgo finally released the data from this particular object, and I'll share the links so that you can take a look at the, at least just skim the abstract of this work. And this is one of the neutron star black hole candidates that LIGO has detected. And so, with the growing number of events, we need to have automated infrastructure to enable this discovery. You need to develop tools that that'll tell you when a binary merger could have an electromagnetic counterpart. So there, for example, here in the pictorially, you saw that video of 2 binary neutron stars colliding and having an electromagnetic signal. But in case of a neutron star black hole system, it depends on the properties of the neutron star and the black hole. In particular, if the black hole is too big, what happens is that the neutron star is swallowed inside of the black hole immediately. It doesn't. You need the neutron star to be disrupted, to be torn apart, for that debris to fall out, to have radioactivity to power the kilonova. And that cannot happen if the black hole is too big. But if the black hole is less massive and is spinning, then chances of that happening does go up. So you need to build tools that will tell you that from the data in real time. And then the other thing I'm more recently working on is the prospect of doing cosmology. So here, let me give you a little bit of a background over here. So cosmology essentially is the inference of certain parameters that describe how our universe is evolving. One of them is what is called the Hubble constant, which is essentially the expansion rate of the universe. And the way it is typically measured is using what are called type 1a supernova. And the other traditional way of measuring it is from this so-called cosmic microwave background. So supernovae and cosmic microwave background are 2 different independent sources to measure this Hubble constant. At least until today, or rather, if you go back, 10 years, then the state of experiments were such that both experiments said that the value of the Hubble constant is order 70, but then the error bars on them were such that you couldn't really tell it apart. So maybe it was 70 plus minus 10. But then with more advanced technology, what has happened is that the supernova value, the error bars have shrunk for both the cases. And then at this point, there is a tension in the value of the Hubble constant. It is not by much. Maybe the supernova, they say it's 71 minus order, say 2. But then the same value inferred from the CMB is order 68. But then, at this point, there is a debate as to what is the correct value. Now, whenever you have something like that, an independent way to measure, the cosmological parameters would be great to have, and gravitational waves do enable a measurement of the Hubble constant. So that is also something I am working on at the moment, and so and I'll just skip over this. This is also some work that I'm doing on photometric classification. So I think I'm pretty much out of time at this point. Yes, I've gone 5 minutes on top of the hour, but I'll end by saying that there is a difference in the way that we do science today that has changed over the years, and maybe it has not permeated down to what is in our education system. There is essentially that. So overall, there has been a boom in observational and experimental science, and we solve. There has been a shift in work culture essentially. So we solve much harder problems. If you think about, I mentioned to you about LIGO. You have to really measure lens out to great precision, which you could not do without the technology that's available today. and science is more interdisciplinary than it has ever been before. So you mostly have very collaborative science. So you have LIGO, but then at least in terms of astrophysics, I would just mention a few other collaborations. The Large Synoptic Survey Telescope is a telescope that is coming up, and whenever it's a next generation telescope, it uses technology that has not been used till date. So it will see objects much deeper than any other telescope has ever done. And whenever there's a shift in technology, you automatically find things that you have not predicted, and that's basically the era we are at. A few other mentions at CERN you may have already heard of. The Event Horizon Telescope is an experiment to image the black hole at the center of our own galaxy. Some of you may know of it. They released there was some interesting work that the EHT collaboration released recently. CMB Bharat is a cosmic microwave background in India, which is coming up. SPT is also a CMB mission in the South Pole. NGVLA is a radio telescope. Nanograv is another gravitational wave effort that tries to measure gravitational waves using pulsar timing. So basically, I guess I'll just reiterate the fact that there has been a shift in work culture, and science has become much more collaborative. And the role of computing is maybe greater than it has ever been before. And so I'll just allude to that point a little bit before ending. Maybe computing should become a part of our curriculum as much as any of the other topics such as science or literature. As a student, if you do get a chance, I would say latch onto that. And at the same time, I would say even if you don't have a chance, there is online resources have been there has been a boom in online resources available today as well. And so if you don't have maybe a good computing class in your school, do make use of those resources, because there is a lot available out there. And then finally, I would like to end with saying that I really appreciate the efforts of Cheenta towards this. I really like the fact that there is focus on data analytics and statistics and machine learning. That sometimes I just hear stories from Oshoni, and I'm really happy that Cheenta is taking in that direction. So with that, I'd like to end and thank you all for having me. Hope that was useful. So at this point, we have gone over the hour, but I'll just stop sharing, or maybe I'll just exit out of the full screen and then check if there are any questions.
Okay, so thank you, Dr. Deep Chatterjee, for his very good and precise talk. So I would first like to ask the viewers or the listeners to this talk, if they have any questions, they're free to ask now. After that, I have a couple of questions of mine. If you have if you have asked yours, lastly, I would like to ask a couple of questions of mine. So it's all to you. Is there any questions? So I think there were some questions in the StreamYard.
Unfortunately, I cannot see the chat, so you could either read out.
Yeah. So Simran, could you just read it out?
I don't know. I don't know if I totally understand that question, but then we are definitely in reality. I would say there is. If you mean that it may seem that some of these experiments, potentially could have been seemingly unreal, maybe even a few decades back, but then it's definitely a reality. I don't know if that answered the question, but I think that's that. Pardon me, I didn't catch that. Okay, yeah, so that's a good question. So a gravitational field is essentially a concept that is present in Newtonian gravity when you consider gravity as a force. In the way gravity is perceived in general relativity, gravity is no longer a force. It's rather this curvature in the object that we all live in, which is called space-time. And gravitational waves are essentially ripples on that space-time, which happens when masses move in that object. So that's the difference between a gravitational field versus a gravitational wave. Gravity is neither a wave or a force. It is the curvature of space-time. So the idea of gravity being a force comes from Newtonian physics, where you have a potential which exerts a force. But then, in terms of, at least in the language of general relativity, gravity is essentially the curvature of this object called space-time that we live in. So gravity is not to be interpreted as a force, but the curvature of this object called space-time that we live in. Not that I know of.
Okay, so I would like a question. I mean, which kind of, I mean, I have a little bit of personal interest in. So see, I mean, like,
Yep, go ahead.
Yeah. So, like gravity, the way I understood, and from some YouTube videos and I mean, like some popular PDFs, it's something like that. That it is mentioned like this: if I have a trampoline and I just put a weight I just put a weight in the middle of the trampoline, and the trampoline is kind of going downwards. So that's kind of the gravity that they have actually mentioned. So now, and you have also said that it is the curvature of the space time, right? So generally, we have the notion of curvature as the what can I say, as the normal vector. I mean, the way the normal vector is kind of shifting, right? So like the sphere, it is I mean, the sphere has a proper orientation, because if I start with the north pole from the if I take the normal vector at the north pole, and if I just go from the north and come back to north, then the normal vector will be directed at the same I mean, it will be the outward normal vector. So so for me, the curvature is kind of like this, that the change between the normal vectors. So if the normal vectors, I mean, the angle of change between the normal vectors locally. So is there, I mean, so like for space time curvature, I mean, how is that related? So I mean, like, will this curvature is some kind of a fourth tensor that we talk about, or?
That is exactly correct. So yes, I mean, without going into a lot of technical details, yes, indeed. So pictorially, if you think about it, I think the picture that is there, the usual depiction of gravity as, you have a trampoline which is a sheet that is essentially flat, and then you put a ball. Now there's a little bit of a it's not entirely correct, because in that case the ball essentially, because of gravity, it causes the sheet to curve, but the idea is similar. It's true that when you do have matter, it will bend the space-time around it. So straight lines are no longer straight in the Euclidean sense. So it's straight in the same sense as if you always lived on a sphere, then if you and your neighbor, both of you started traveling towards the North Pole, then by the time you reach the North Pole, you would find that you two are closer than what you originally started off with. Now, instead of actually physically traveling to the North Pole, you consider that that's traveling in time. Then with time, you two have come closer, and that can be interpreted as a force of gravity. So the idea about carrying a stick around and trying to measure this change comes from that fact that we all live in this object called space-time, and then that space-time has some curvature based on whatever matter density there is, and it's in space-time abstractly. You cannot perform an experiment where you actually take a stick and you move it around space-time, but then that's the mathematical concept that if you did take a stick and if you parallel transported it around a loop and you brought it back, and if there's a non-trivial shift in the direction, then that is caused due to curvature, and what general relativity says is that curvature comes from matter.
Right. Thank you. So so I mean, it's kind of like the exact same curvature that we have. I mean, if I want to go into a little bit of detail, like the exact same curvature that we have for manifolds, right? So fine. Thank you. So I have asked my questions. So if anyone else have any questions, they're free to ask. Okay, fine. So if there's no question, then let's thank the speaker. Thank you for joining us for today. So hopefully we will be in touch.
Absolutely. And sometime later, whenever I have time in the day, I'll forward the link to my slides in case anyone is interested to take a second look at the videos or read some of the articles. They could do it then. I'll forward the link to Astronomy, and maybe you could distribute it to the interested. It's okay.
Thank you.
All right. Thank you.